Testing, testing. Can Zoom audience hear me? Can get a thumbs up if you can hear me. Yeah. All right. Thanks. Okay. So, better? All right. So yesterday was parameterized algorithms day. And if you remember back to day one, I had to look at my notes to remember back to day one. You'll remember that I introduced you to linear programming and integer linear programming. And hopefully you still remember that from 2 days ago, because today we're going to be doing that on steroids in order to design some cool approximation algorithms. So we're going to be looking at problems on strings for once. Most of the time we're going to be looking at graph algorithms, but now let's do something different. So for two strings, S1 and S2 on the same number of characters, let's say L, we'll define the Hamming distance between them to be the number of positions where they differ. So you compare the first letter of the first string with the first letter of the second string, the second letter of the first string with the second letter of the second string, and so on, and you just count how many positions where they differ. So for example, the distance between horse and force is 2 because H is not equal to F and S is not equal to C. Yeah. We can extend this notion of distance from just a pair of strings to distance from a set of strings to a string, which will now be just the distance to the string from the one in the set that's furthest away. That's how we define it. So if I want to find the distance from a set of strings to just one, I'm going to count that as being not the average, but not the minimum, but the maximum distance from one of the strings in the set to the center. And the way we think about this is that you have the set, and you can think of, if these are binary strings, you can think of them as points on a hypercube, right? And then this center string C will be also a point in the hypercube, and then you're interested in, well, how big of a ball around the center do you need in order to cover all of the strings in your set? That is the distance from the set to the string. Now, in the closest string problem, input is n strings, all of the same length, all over the same alphabet. Think of the alphabet as being a constant, but it doesn't have to be, right? So if it's a strings over the English language, then it's an alphabet of size 26. If it's binary strings, the alphabet has size 2. If it's genomes, the alphabet is ATCG and has size 4. Now, input is a set of n strings, each one of the same length L. And the task is to find a single string, a center string C, also of length L, that minimizes the distance from the center to the set. Right? So you're trying to find a single string so that the smallest possible ball around that string will cover the entire set. Okay, so for a sanity check, if the center is required to be in the input set, is this problem polynomial time solvable or NP complete? So if the center string C is required to be one of your input strings, a string in S, is the closest string problem then polynomial time solvable, or is it NP complete? It's polynomial time solvable because I can just loop over each of the n options of strings in S. For each string, compute its distance to the other strings. That is, of course, a single for loop over the character position, so that takes polynomial time as well. And then pick the candidate out of the n candidates with the smallest maximum distance to the other ones. Now, in the closest string problem, C is not required to be one of the input strings. And then the problem actually becomes NP complete because at every character position, you have at least two options. If the alphabet has at least two letters, you choose either A or B at every position. So you have at least 2 to the power L options for what your center string should be. And you can, in fact, show that this problem is NP complete. Now, what we're going to do is to ask, well, what is the best we can do in polynomial time? Can we get an approximation algorithm? And in fact, we're going to get the best type of approximation algorithms one can hope for, namely a polynomial time approximation scheme. So an algorithm that for every fixed epsilon greater than 0 will find a 1 plus epsilon approximate solution in polynomial time. Yeah. The reason this doesn't prove that P is equal to NP is that the running time is something like n to the power 1 over epsilon. So if you set epsilon to be a function of n, make it arbitrarily small to make your approximation scheme to actually find exact optimum solutions, then this will give you exponential running time for your algorithm. Okay. Nevertheless, for 1.1 approximation, we can do it in polynomial time. 1.01 approximation, we can do it in polynomial time. 1.00001, your favorite number of zeros, we can still do it in polynomial time. This algorithm consists of two algorithms. One that is actually quite practical and works really well. And the other one is a ridiculous algorithm that works for the pathological cases where the first algorithm doesn't work. Okay, so first, let me tell you the one that is practically relevant. So let's formulate an integer linear program for closest string. All right. So remember, what are the decisions that we have to make in order to find a center string? Well, for every position from 1 through L, we need to decide which letter should the center string be, right? So a fairly reasonable way of encoding this as an integer linear program is to have an indicator variable that is either 1 or 0, depending whether the center string is that letter at that position. So for every position I and every letter alpha, let's have the variable xi alpha, which is either 0 or 1. We encode that with a linear constraint that is between 0 and 1. And we will interpret it being 1 as setting the center string at position I to the letter alpha. Now, what should the constraints be? Well, at every position, we should pick a letter. And we should pick exactly one letter. So how do I encode this as a linear constraint? So you're saying the summation of xi alpha over all I should be equal to L. That is correct. That tells you that you have to pick L letters, but it doesn't and it won't constrain you to pick one letter at every position. Yeah. So for every I, if you sum over all alpha of xi alpha, that should be equal to 1, right? So here it is. For all I, if I sum over alpha in the alphabet of xi alpha, then that should be equal to 1 because I pick one character at that position, and for all of the other ones at that position, they are not picked. Okay, now here is an interesting question. How do I encode distance, right? Because that is what I'm trying to minimize. Right now I've encoded this thing that, well, in like my x variables, they encode the choice of the center string. But now for every string s in my input, I need to figure out what is the distance from S to the center string that I chose, right? And now here is a simple observation, and this is that if my string, if my string S is ABC, then at the first position, if x1a is not equal to 1, then that should contribute 1 to the distance from the center string to S, right? So in particular, when I'm calculating the distance from the center string to S, this is nothing but the sum over all positions of 1 minus the indicator of whether the center string was set to the character of S at position I. Yeah, you pay 1 unless you set the center string to just the right character. Yeah. Now, we are not interested in just the distance from the center string to S. We're interested in the maximum distance from the center string over all choices of S. So if we now have a new variable that we call D, that is now on the right-hand side of our inequalities. When I introduced ILPs, I only had constants on the right-hand side of the inequalities. Of course, that is not a problem, right? I can write the inequality with a variable on the right-hand side, but then when I try to feed it to my solver, I just move it to the left with a negative coefficient and put 0 on the right, yeah? But it's more convenient to write it in this way. So we have now that for every string, the distance from the center string to that string should be at most D. Yeah. Okay. You can now convince yourself that that is enough to encode closest string as an ILP. In particular, you know, every center string corresponds to a feasible solution to an ILP with the same value. Every feasible solution to the ILP corresponds to a center string whose distance is precisely D. We can't solve the ILP, but we can solve the LP. So let's solve the LP, right? Relaxation in polynomial time. And we get optimal values for the xi alphas and D, except that the xi alphas now aren't 0, 1 variables. There's some weird thing between 0 and 1. I pick this letter 0.2, that letter I pick 0.5, etc. All right. Now the question is, how do you round? Right? A fairly natural thing to do, this would be probably the first thing I'd try if I saw this, was that, well, at every position, the LP variables vote which character you should take, right? Like you should take, for example, if your possible characters are A, B, and C, and the vote for A is 0.5, for B 0.25, for C 0.25, it's fairly natural to say, okay, let's take the majority vote, right? Like take the character that the LP variable is the biggest for. Unfortunately, that doesn't quite turn out to work. Maybe I'll, Neil, for tutorial question, make an instance where that doesn't work. So what we're going to do instead is to do a randomized algorithm. In particular, notice that at every position, the sum of the LP variables is equal to 1. That's a probability distribution, right? Whenever you have things between 0 and 1 that adds to 1, it's a probability distribution over characters. So I can sample characters from the probability distribution according to the probabilities that are given to me by the LP variables. So in the first case where if LP variable for A was 0.5, B 0.25, C 0.25, then that's the probabilities with which I will pick A, B, and C at that position. Now notice that the probabilities are different at the different positions, and so I'm going to use the LP variables for position I to figure out with which probability I should sample the respective characters at each position. So that's what we're going to do. Yeah. So for every I, we're going to set C of I to be equal to alpha with probability xi alpha. Okay, now let's analyze this, Because, well, we know that we always get some string of length L, so we always do get a feasible solution to our closest string input. So now all that we have to figure out is, well, how good is it? Right? How far is it from the set S, and how far is it from the set S when you compare it to the optimum center string? What are we going to do? Well, just as we always do, the first thing we're going to do is we're going to compute the expected distance from the center string C that we're outputting to the set to a fixed string S. Yeah. So fix some string S in the input. Now C is a random variable because we're picking it at random. Therefore, the distance from C to S is also a random variable. It's integer valued, so we can compute its expectation. How do we compute its expectation? The same way we always compute expectation, using the method of indicator random variables. Okay, so what should our indicator random variables be if we're trying to compute the expected distance from C to S? Exactly, right? So if the distance is just the number of positions where the characters are different, therefore, if for every position we have a variable that is 1, if the characters of C and S are different, and 0 if they are the same, then if you add up the indicator random variables, you're going to get precisely the distance. Yeah. Now we ask ourselves, for a given indicator, what is the probability that that indicator is 1? Well, I'm going to set C at position I to be equal to Si with probability Xi Si. So the probability that it is different is 1 minus Xi Si, right? So by linearity of expectation, right, the expectation of the distance is the sum of the expectations of all of the indicators. The expected distance is the sum from 1 minus Xi to Si, but that was precisely how we computed the distance between C and S in the LP, so that just by that constraint, where is it, is at most D, right? Because we forced D to be bigger than that value in the LP. And now that holds for every string S, right? So for every string S in our set capital S, the expected distance from the center string to that string is going to be at most D. And D is, of course, our opt LP, right? So remember that D is the thing that we're minimizing, right? So D is equal to opt LP. And so for every string, the expected distance from it to any string, any fixed string in our set S, is at most opt LP. Okay, so we were here. So now, what happens is that this is a sum of independent 0, 1 variables, right? And therefore, we can apply Chernoff bounds. Right? I think I did teach you Chernoff bounds already, right? I hope I did. Okay, yes. Good. All right. So when do Chernoff bounds apply? Chernoff applies when your value is a sum of independent 0, 1 variables, right? So Chernoff applies now not to the maximum distance, because that is the maximum of sums of independent 0, 1 variables, but it applies to independent distances from the center string to a single string in your input. So now again, let's analyze the distance from C to a fixed string S in our input. We know that the expectation is at most D. Now we ask, what is the probability that it is much bigger than D? Well, in fact, rather than asking what is the probability that it is much bigger than D? Well, we know that D is equal to opt LP. And opt LP is less than or equal to opt ILP. And opt ILP is just equal to opt for our center string problem. So we want to give our rounding a little bit more leeway, right? We're shooting for a 1 plus epsilon approximation algorithm. We can allow the distance from C to S to be 1 plus epsilon opt. So the event we're interested in is, what is the probability that distance from C to S overshoots opt by at least epsilon opt? That's the bad event that we're trying to upper bound the probability of. And now we know that opt is an upper bound on the expectation of the distance. And therefore, this handy version of Chernow, where we can plug in the upper bound, both in the bound here, like both in the description of the bad event and in the exponent of the probability, that one applies. And it turns out to be really useful because now the probability of the bad event is inverse exponential in opt, right? It's 1 over e to the power opt, like 1 over e to the power opt, times some constant factor that depends on epsilon and 3. Yeah. Constant factor that depends on 3 is a constant factor. Okay. Now here's, so notice that for each individual string, you're not going to overshoot opt with very high probability, or you're overshooting opt with very low probability, with exponentially low probability in opt. But that's just for a single string. You want to not overshoot 1 plus epsilon opt for all of the strings, right? So you now have n bad events, 1 for every string in your input. And what do you do if you want to upper bound the probability of a bunch of bad events happening? Just apply the union bound, and you sum the probability. So by the union bound over all the n choices of S, the probability that at least one of the bad events happens is n divided by e to the epsilon square opt over 3. And now, if this is less than 1/2, we win. If it's more than 1, we lose, right? So let's figure out, well, when is this less than 1/2? Well, okay, we need n over e to the epsilon square opt over 3 to be at most 1/2, multiply by the denominator, take logs on both sides, and you end up with something like this, that opt needs to be at least 3 times log n over epsilon squared. Yeah, there's nothing interesting happening here, just math. So in particular, as long as opt is super logarithmic in the number of strings in the input, then our LP rounding algorithm already works, which means that most of the time this is going to work, right? Like, unless you get an input where the closest string is really, really good, yeah, your LP rounding is actually going to be doing great. It only fails if there exists a solution that is really, really good, and then the error of your LP rounding might overshoot that. Okay, so now what we have to figure out is, well, what do we do when opt is really, really, really small? Right? Well, if opt is at most log n, and we can afford polynomial time, then we can afford to have algorithms that run in time 2 to the opt. Because if opt is log n, then 2 to the opt is 2 to the log n, which is polynomial in n. In fact, since we can afford time n to the 1 over epsilon, we can even afford running times on the form like 1 over epsilon to the order opt. Yeah, because that's 2 to the power log 1 over epsilon log opt. You pull log opt out, you order opt, which is log n, you pull log n out, and you get n to the log 1 over epsilon up top. Yeah, so this is, for example, the calculation right here. Because if opt is ln n divided by epsilon square, then this is e to the ln of 1 over epsilon times ln n over epsilon square, which is n to the natural log of 1 over epsilon divided by epsilon square, which of course is polynomial when epsilon is a constant. Okay, so now we're going to do the ridiculous algorithm, which is a 1 plus epsilon approximation for this problem, whose running time is polynomial n, and his success probability is essentially 1 over e to the opt. Yeah. Okay, now the first thing is, suppose we know opt. And when I say suppose we know opt, I don't mean we actually know the correct center string. Suppose we know the distance from the center string to the string that's furthest away. Suppose we know the value of opt. Okay, what do you do if you don't know it? Pardon? Yeah, so you just repeat the algorithm for each possible value of opt. 1, 2, 3, 4, 5, 6, and so on. And then for one of the values, the algorithm is going to give you like the correct string, right? For one of the values, your assumption applies. And for that one, you're going to get the reasonable string. Okay, so we assume that you know the value of opt. And initially, you're going to set your center string as some string in your input. And then you do the following for a while. For a while, they say as long as the length of your strings. If your current center string is already an approximate solution, you can output it, right? If it isn't already an approximate solution, then there is some string in your input which is at least 1 plus epsilon opt away from it. Now notice, this is the place where we're using that you know opt. You're checking like if the distance from C to S is at most 1 plus epsilon opt, you output the string. That's the only place where we're using the assumption that you know opt. Good question for the tutorial. Modify this algorithm to an algorithm that works without knowing opt, without also having to run over all versions of opt. Neil, please. Thank you. Okay. What are we going to do? S is some string that is furthest away from it. It's at least 1 plus epsilon opt away from it. And now you look at the positions where S and C differ. There's at least 1 plus epsilon opt of them. And what we're going to do now is we're going to select one of these positions uniformly at random, and we're going to flip the center string to S's character in that position. Notice that at least one of these positions, I have to change the center string to what S is in one of those positions, because if I don't, the distance from my center string to S will stay more than 1 plus epsilon opt, right? I know that at least for some of them, I have to fix it. So I pick a random one and I fix that one. And you just keep doing this for a while. If at any point your center string becomes a 1 plus epsilon approximate solution, you output it. And if it doesn't, after you've tried for L times, then you don't and you return fail. Yeah, so that's the algorithm. Now this algorithm always runs in polynomial time, right? Because you just have a for loop that goes over all characters. It doesn't do any sort of exhaustive search inside the for loop. It just picks something at random and flips a character in C. And if the algorithm doesn't fail, it returns a 1 plus epsilon approximate solution, right? So in particular, all we need to do in order to show that this is a 1 plus epsilon approximation is to prove that the probability that it doesn't fail is sufficiently high. Okay, let's do it. Let C opt be some unknown optimum solution. So we're going to analyze our algorithm with respect to some unknown optimum. And we're going to say that the algorithm succeeds in step I if in step I, the center string moves closer to C opt, right? Like if you flipped a character that at C that wasn't equal to C opt to something that was equal to C opt, let's rephrase it. If for the selected position P where we flip, if S of P is actually equal to C opt of P. Remember that S is the string that is far from our current C, and so we're flipping C of P to S of P. Yeah, so if S of P is equal to C opt of P, then after this step, C of P will be equal to C opt of P, while it wasn't before the flip. Okay. I already explained that why it holds that if the algorithm succeeds in step I, then the distance from C opt to C decreases by 1 because you flipped a character that was different to one that is the same. And now all we're left with doing is to show that the probability that the algorithm succeeds in step I in any given step is relatively high. Okay. So what's the probability that the algorithm succeeds in the first step? Yes? This. We're saying, we define success. We say that the algorithm succeeds if, for the position where you select to flip, S of P is equal to C opt of P. Yeah, and this is an equivalent definition to saying that in this step, the distance from C to C opt decreases by 1. Yeah? Pardon? The distance from C to C opt. Yeah, I probably misspoke. The distance from C to C opt decreases by 1 because C opt is fixed. It's some unknown optimum solution. S is fixed. It's your input. The only thing that changes is C. It's your candidate center string, right? So the distance. So you're succeeding if C gets closer to C opt. Imagine you have some ball. C opt is there in the center. In the beginning, C starts off somewhere, and now it's moving, and you ask, is it moving closer to the center? Yeah? Pardon? No, S here should be S. I mean, the definition is correct the way it says. If S of P is equal to C opt of P, then after that iteration, C of P will be set to be equal to S of P. Yeah? Okay, so now all that's left to do is to figure out what's the probability that the algorithm succeeds in any given step. Let's say the first step. Okay, now, well, the probability that it succeeds is the number of positions where it would get closer divided by the number of positions that it has to pick from, right? So, okay, let's analyze those two, right? And in order to analyze those two, what we need to do is we need to just look at the three strings, C, S, and C opt, put them, next to each other or on top of each other, and compare where they differ and where they're equal, right? So first, let the red positions be, let's see. Yeah, no, sorry. Let the green positions be the positions where C differs from S. Yeah, that's our set Z. Yeah, we found S because it differed from C in many positions, at least 1 plus epsilon K opt in this case. At least 1 plus epsilon K is easier. Okay, from Z. Okay, Z is at least 1 plus epsilon opt. Let me fix this. This minus should be a plus. There we go. Okay, so we have these green positions, and we're picking a random position out of the green ones to flip C to be equal to S at that position. Now, the red positions are the ones where S differs from C opt. Yeah, and now here's the thing. There are at least K into 1 plus epsilon green positions, because that's how we picked S. Right? We picked S because C wasn't 1 plus epsilon approximate solution. Therefore, there are many places where C and S differs. At many means at least K into 1 plus epsilon. Now, there are at most K positions where S and C opt differs. Because, yes, K is equal to opt, yeah. Because, you know, opt is an optimum solution, so the distance from opt to any string in the input is at most K. Yeah. But then there are at least epsilon K positions that are green and not red. Yeah. Okay. So in particular, there are epsilon opt positions up top, and I claim that there are at most 2 times opt positions at the bottom. So Z is at most 2 opt. Well, Z should actually be, yes. Okay, that's, why is Z at most 2 opt? Right, so if you remember, what are we trying to say here? Right, we're counting the number of good positions. So the numerator we now said was at least epsilon opt. And I'm now claiming that the denominator Z, the set of positions where C and S differ, in the first step is at most 2 opt. Why is that? Right, I'm claiming that Z is at most 2 opt. Why is that true? Pardon? So Z is the set of positions where C and S differ in the first step. I claim that this is at most 2 opt. Why? In the first step, C is one of the input strings, exactly. And now you apply triangle inequality. The distance from C to C opt is at most opt. The distance from C opt to S is at most opt. Therefore, the distance from C to S is at most 2 opt. So Z has size at most 2 opt. So in the first step, right, in the first step, the size of Z is at most 2 opt. Therefore, our success probability is at least epsilon opt divided by 2 opt, which is at least epsilon over 2. Pardon? Yes. Which equality? This, yes. Well, yes, this equality should be greater than or equal to. Yeah. There we go. Okay. All right. Now, what is the probability that the algorithm succeeds in step 2? Well, the numerator is again at least epsilon opt. What about the numerator? Well, you went closer to C opt, right? You were at most opt away from C opt before. And if you succeeded, like given that you succeeded in the previous step, you are now closer to C opt. So Z is still at most 2S. Yeah. So the probability that you succeed in the second step, given that you succeeded in the first step, is again at least epsilon over 2. The probability that you succeed in the third step, given that you succeeded in the first 2, is again at least epsilon over 2. So now, what is the probability that you succeed in the opt first steps? Well, epsilon over 2 to the power opt. But what happens if you succeed in epsilon? What happens if you succeed in the opt first steps? Pardon? You get the optimum solution. Then C is equal to C opt, right? You started at most opt away. In every step, you moved one step closer. So after opt successes, they're equal. And when they're equal, of course, the algorithm will terminate. So the algorithm will terminate before you have gotten opt successes, right? Which means that the algorithm is going to terminate and output some string with probability at least epsilon over 2 to the power opt. Yeah, so that's the success probability of your algorithm. Just if you want to have better success probability, then repeat epsilon over 2 to the opt many times. Yeah, then you get success probability 1/2. Now, here's the combined algorithm for closest string. If 3 ln n over epsilon squared is at most opt, solve LP and round. Right? Otherwise, do local search algorithm. And what is the running time of the local, or otherwise do local search algorithm repeated many times. What is the total time after all of the repetitions? Well, it's 2 over epsilon to the power 3 ln n over epsilon squared, which is n to the ln 1 over epsilon divided by epsilon squared. So for every epsilon, you get a 1 plus epsilon approximation in time n to the power some function of epsilon. And now notice that in all except like in the very small opt case, your algorithm is now taking super polynomial time because you need to repeat it a bunch of times. But in the non-pathological case, when opt isn't really, really good, your algorithm actually just runs in normal polynomial time, right? Like whatever time it takes to solve an LP and round. Okay, so we're going to switch problems now. So feel free to ask some questions. Go over the ILP again? Okay. Is equal, yeah, it's less than or equal to opt. Let's see. Yeah, so here. So first we have a variable for every position and character. Is the center string equal to that character at that position? For every position, we need to pick a character. So with the sum of characters for every position is equal to 1. And you encode distance by saying that the distance from the center string to S is the sum over all positions of 1 minus the indicator of whether you picked that character at that position.
Okay, calculation shows it, but the random process of picking C using randomized sampling,
yes,
picks a valid solution, right?
Yes.
And
so the point is that the point is that the reason the problem is NP hard is that you have many strings, right? Now, if you have some probability distribution and you have some expectation, yes. If your probability distribution is like somehow normal, right? Like somehow symmetric, right? Then with probability 1/2, you'll be above the expectation. With probability 1/2, you'll be below expectation, right? Your good event, if if you're trying to actually find an optimum solution, then what you want to happen is that for every string, you want to be below expectation simultaneously. And if this is something that happens, independently even for n strings, then your probability of being below opt for all n strings simultaneously is inverse exponential in n. Okay? So even though your expectation is really, really good, the probability of achieving expectation simultaneously for all the strings is really low. More questions? Yes. Well, it will be a factor 2 approximation. Yeah. It's not arbitrary bad, but not the 1 plus epsilon. Okay. Correct. Yes. So for for each individual string, the expected value from the distance of center to that string is at most LP opt. That's somehow the key. Okay. So all right. So new problem. And if you thought this was too easy, it's going to get harder now. So and I do expect to actually use more time than there is in this lecture. But the next one I expect to be shorter than 90 minutes. So I'll probably spill over into the next one. And so you'll have to try to remember where we stopped over lunch. Yeah, so that will be a challenge. Okay. Okay. So here is one thing that I actually do want you to remember from this class. This is a version of Chernoff bounds that is really useful when your random variable is a sum of independent things, but they are not 0, 1 random variables, right? Like Chernoff applies when you have a sum of independent 0, 1 variables, but there's lots of times you have a variable that is a sum of 0, 2 random variables, or 0, 1, half 1 random variables, or something like this. And then it's really nice to have some sort of more general form, and that general form is known as a Hofting bound. So if x is a random variable, which is the sum of independent random variables x1 through xn, such that each xi has an upper bound and a lower bound, the lower bound of xi, like xi is between ai and bi. Yeah. Now think of bi minus ai as being some tiny constant, like 1. Right? Like if bi minus ai is 1, then this essentially reverts back to Chernoff bounds. I mean, not quite, but essentially this does. And your xi's are independent, then the probability that x differs from its expectation by at least something is inverse exponential in something squared divided by the sum of the squares of the difference, like the size of the squares of the range sizes. So if each range for each xi is a constant, right? Like if each xi is a 0, 1 variable, then the square of bi minus ai is just 1, and you're dividing down by n, right? So now you're thinking, okay, you're dividing down. So in the exponent, you're doing the deviation squared divided by n. Yeah. So if your deviation is on the order of n, if your deviation is like epsilon n, then you're getting epsilon square n square divided by n. So your inverse exponential in epsilon n. Yeah. So that's like a good sanity check to do, right? Like what happens when you care about deviations that are linear in the number of random variables? Yeah. But you still get meaningful bounds even when your deviation is like, as long as it's bigger than the square root of the number of random variables you have, then Hofting is going to give you some meaningful results. So in this case, it doesn't really matter. I probably should have put greater or equal to, yeah. It's probably a lack of care on my end, and I'm not going to like go out here and claim that you could have just as well have put less than or equal to, but I'm like 95% sure that you could have. Yeah. Okay. Yeah, with high probability. Okay. Yeah. All right. So let's look at this problem that we've seen before. This is one problem that we're going to see at least 3 times in this class, maybe 4, namely max cut. Okay, so I give you as input a graph G, and you want to find a partition of the vertex set into a left part and a right part, maximizing the number of edges that go from left to right. Or in other words, you want to find a set S, let's say just the left part, maximizing the number of edges, or you want to find a set S maximizing d of x. That's wonderful. You want to find a set S maximizing d of s, or a set x maximizing d of x. Those 2 letters should have been the same. But now we're going to have an additional assumption, and that is that the graph has large minimum degree. So it's one of those interesting situations where the problem actually becomes easier if the graph is really dense, right? Like usually when the graph is Like you think of the sparse case as the easy case and the dense case as the hard case. This time is kind of the opposite. So from the perspective of trying to approximate max cut, if the graph is dense, you can actually approximate max cut really well. So what we're going to do is that for every c greater than 0, if the minimum degree is at least Cn, right, we will find a 1 plus epsilon approximation in time n to the order 1 over epsilon squared times c, or something like that. Okay, for the purposes of this talk, think of c to be equal to 1/2. Everything we say will work for any other constant c, but really just think that every vertex has edges to at least half of the other vertices. Okay. Now, here is an easy observation, and that is that m is at least Cn squared over 2. The number of edges is quadratic in m. Why is that? Because, the sum of the degrees is c times n squared, and the sum of the degrees is the number of edges over 2. And we showed in the first lecture that there always exists a cut that cuts half the edges. Right? So opt is at least Cn squared over 4. Right? So what we're going to do, we're going to shoot for an algorithm that produces in polynomial time, like n to the 1 over epsilon squared or something like that, a cut that is an additive epsilon n squared approximation, right? So it's off additively from the optimum by epsilon n squared. And now, for some other choice of epsilon, if I choose epsilon to be epsilon over 10, then this will be a multiplicative 1 plus epsilon approximation. Any questions to this? Okay, so I'm saying that because opt is large, right? Opt is at least n squared over 10. Yeah, that means that if I differ from opt additively by at most n squared over 100, then I am a 1.1 approximation algorithm. If I differ from opt by at most n squared over 1000, I am a 1.01 approximation algorithm. So in general, in order to be a multiplicative 1 plus epsilon approximation, it's sufficient to be off from opt additively by some epsilon prime n squared. Yeah, so that's what I'm going to be shooting for. I'm just going to be from now on, I'm just going to shoot for being off additively from opt by at most epsilon n squared. No, so the assumption we made is that every vertex has degree at least Cn. So we're doing max cut in graphs of high minimum degree. Yeah. Okay, so without loss of generality, the optimum solution x opt satisfies that the size of x opt is at least n over 2. Why is that? Exactly, right? Like if I have a really small cut, then taking the complement set, like the remaining set, is also a solution with the same quality, right? If I have a left side and a right side, and the left side is small, then the big side has the same cut. Okay. Now let x be the size of the cut. We can assume that we know it. Well, we already looked. We can just try all possibilities, run the algorithm for all choices of our guess, and then for one of them, it's going to be correct. Okay, so let's start. What does the algorithm do? It samples a set S on log n over epsilon square many vertices from the VG, and it defines d hat of V to be S intersection n of V divided by S times X. Okay, some crazy number. So what is it that we actually want to happen? When we sample S uniformly at random from the vertices, the good event that we're interested in is that our sample is all sampled from the optimum solution. What is the probability that our sample is taken from the optimum solution? Yes, so that's a like the correct bound. I want a rougher bound that's easier to work with. Well, x is, or x opt is at least n over 2, right? So each element of S is an x with probability at least 1/2. So the probability that all of them are in S is at least 1 over 2 to the S. And S is like ln n over epsilon squared. So this probability is something like n to the 1 over epsilon squared. Yeah, so it's inverse polynomial. So with, small but not crazy small probability, I'm actually sampling S entirely from within my optimum solution. And now I'm just going to assume that that good event happened, and I'm going to condition everything based on that the sample is sampled from opt, because now I can assume that once I condition on S being a subset of X, or a subset of X opt, S is now being sampled uniformly at random from the optimum solution, which I don't know. Yeah, so here's this wonderful thing that if I have a big graph and in it there is some optimum solution that I don't know, but it's big, then when I sample uniformly at random, with good probability, my sample is inside that solution. And now I can pretend that I'm sampling uniformly at random from that solution, even though I don't know it. Okay, so now what's going on? I'm picking my sample uniformly at random from my solution. So the left side on this picture is X opt, and I expect my entire sample to be on the left side, inside X opt. What I want to do is I want to estimate for every vertex its degree into the optimum solution. That's what I would like to do. And we're going to do like the lion room experiment from yesterday, right? If every lion barks with probability 1/2, and you hear 100 barks, then probably there's close to 200 lions in the room, right? So we're going to do exactly the same thing. When I pick a vertex from my sample, like when I pick a vertex in the sample, I cannot know whether it is in the optimum solution or not. This I don't know, right? I do know whether the vertex from my sample is in the neighborhood of V or not. Yeah, that's my bark. Yeah. Now, if I look at the vertex V and I look at its n of V intersection X, right? Then, so n of V is the gray zone over here, right? Like this is all of my, this is my n of V, yes? When I pick a random element from X opt, what is the probability that that random element will end up in n of V? If I'm picking a single random element from n opt, what is the probability that that random element will end up in the neighborhood? Well, it's n of V intersection X opt, so it's this area divided by all of X opt. Yes? Because I'm picking from all of X opt. That's, yeah. And the probability that I end up in n of V is just n of V intersection X opt divided by X opt. Yeah. So that is my probability of a bark. Yeah, which I don't know because I don't know n of V intersection opt. But if I pick a bunch of samples uniformly at random, and they are all from X opt, then the ratio of the number of samples that barked relative to the number of samples should be close to the probability of a bark. Yeah. So using that, I can now recover the size of n of v intersection x. Yeah. Now suddenly this makes sense. This is the recovery. This is my estimate of what is n of. This is my recovery of what is n of v intersection x based on how many vertices of the sample ended up in n of v. Yeah. Some log n many times. Yeah. So I sample log n over epsilon square many times, and now I count how many times did I end up in n of v, right? Like, so S intersection n of v is the number of barks I observed. Yes, the number of barks I observed divided by the number of times I could have observed the bark. That's the probability of a bark. Yeah, and now I multiply it by the total probability space to say, well, here is the number of points that would have barked in the whole probability space. Yeah. Okay, now let's do this analysis carefully. Yeah, x and x opt is all the same thing. Yes, yes. Well, okay, little x is the size of x opt, which I know. Yeah. So the thing is, I don't know x opt, but I know x, and x is the size of x opt. But you can really just think of them as all as the same thing. Yeah. Yeah. We aren't choosing, we're going to do this for every vertex. So for every vertex, we're going to define d hat of v to be that. Yeah, but it's nice to look at one vertex and then say that we're going to do this for every vertex. Okay.
When choosing n of v independent vertices, it's better to choose v and a stable.
Pardon?
I mean,
no, because we want, so we are going to pick one sample and use that sample to make estimates for all of the vertices simultaneously. Yes? Yeah, so instead of, like, if I wanted to make a sample for v, then I should be sampling from n of v, but I want to use one sample of size log n to get estimates for all of the neighborhoods at the same time. Yeah. Okay, so now here is the thing. When I sample S, yes, what is my expected size of, like, what is my expected size of S intersection n of v? Yeah, each vertex in S will be in n of v with probability n over v intersection x opt over x opt. Yeah, that's the, and now I'm picking S of them. Yeah, so that's the expected size of S intersection n of v. Yeah. So our good event is now that S is in x opt. And the second one is that for every vertex, the n of v intersection x opt is actually close to our estimate, which is equivalent to saying that all of our S's were close to their expectation, right? Like S intersection n of v was close to the expectation of S intersection n of v. Yeah, so a way to rewrite good event 2, which is that all of our estimators are accurate, is just saying that for every v, S intersection n of v was close to the expected value of S intersection n of v. Okay, so now we know that the probability of the first good event, that we sampled uniformly at random from x opt, that's inverse polynomial. Now what we need to do is we need to figure out what is the probability of our second good event. Yeah, that all of the samples are close to their expectation. Well, for that, we first need to figure out what is the expected value of S intersection n of v, given that we're sampling from opt. And for here we have already computed this. this is a method of indicator random variables. What is probability that the ith vertex from the sample comes from n of v? Well, that's n of v intersection x opt divided by x opt. You're multiplying that by s. So the expected value of s intersection n of v, given that you were sampling from opt, is this baby here. Cranky, cranky, cranky. Okay. Now so in particular, what we're interested in, what is the probability that this intersection is close to its expectation? And for that, we can do Hofting. Why? Because all we care about now is what is the probability that S intersection N of V is actually close to its expectation. Yeah, which is at most, so now we ask, well, what is close? Is at least, like, you want it to be at most epsilon S away, right? So the bad event is that you're at least epsilon S away. And what does Hofting say? It says that the probability of being at least something away is e to the minus that something squared. Yeah, so that's where you see the epsilon squared S square down below, divided by the sum of the ranges squared. Yeah, but these are all 0, 1 random variables. So the sum of the ranges squared is just, 1 minus 0 squared, 1 minus 0 squared, S many times. So now I'm just dividing down by S. What am I getting at this point? I'm getting that this is at most 2 to the minus epsilon squared S. Plugging in my choice for the size of S, I'm getting that here now, notice the epsilon squared canceled. This is why I chose S to be ln n divided by epsilon squared. Because when now I'm applying my Hofting bound, I'm getting an epsilon square bound here. Yes, because I want to be only epsilon S away. When I'm squaring that, I'm getting an epsilon square in my exponent. I want the epsilon square exponent to go away, but I have an S which I'm controlling. So now that I'm choosing my S to have a 1 over epsilon square factor, the epsilon square goes away and I'm left with 1 over 2 to the n, like I'm left with 2 over n squared. Okay, what did we just show? We showed that for any given vertex, with probability 2 over n squared, the estimate for that vertex was far away. Yeah, so that's the bad event. Like the bad event that the estimate is for a given vertex is far, the probability is at most 2 over n squared. I only have n bad events, 1 for every vertex. Yeah, Chernoff plus union, Chernoff plus union. Hofting is basically Chernoff plus union. Yes, so apply union bound over all the vertices, and now I get that the probability that for at least one vertex the estimate is bad is at most 2 over n squared times n, so that's at most 1 over n. Yeah, so conditioned on the fact that S was sampled from the optimum solution, the probability of the good event is actually 1 minus 2 over n. So with very high probability, the estimators for all of my degrees into x opt are actually correct. And now by just multiplying things out correctly, what you're going to end up with, okay, let's do it. Yes, for all v, S intersection n of v is close to the expectation of S intersection n of v, right? We showed that the expected value of S intersection n of v was this, but then I know that for all v, the S intersection n of v minus the expectation, which is here, is small, yes, but the left-hand side is now the true value for, what am I saying here? I'm saying something. Am I saying? Did I write something stupid?
I think for the expected value, you don't have to multiply with cardinality of x. It should be x.
I think there should be. So here there should be an x. Yes, because in the right hand, this expectation s of n of v. Yeah, I think I did something wrong in the algebra. So ignore the algebra, right? Ignore the algebra and just listen to the moral, and then you can go back and do the algebra yourself, because I mean, okay, it's good to do the algebra yourself, but if the interesting thing that's going on is that if every estimator is sufficiently close to the correct degree, where sufficiently close means epsilon s, right? Like if you're off additively by epsilon s, then the degree estimators will be off from the correct degrees by epsilon n. Yeah. So the thing that so that's really what you care about. That if the sample size is off by from what it should be an expectation by epsilon, the size of the sample, then you'll end up with the estimators being off by from their true value by at most epsilon n additively. So we can conclude at this point that the following thing happens. Let's see, that the size of the cut is the sum over all the vertices that are not in X of their degree into X. This is how we're going to count the cut. Yeah? But, yes? So, okay, what is the cut? We have the sum set X, and we're looking at all of the edges that have exactly one endpoint in X. One way of counting that is summing over all vertices that are not in X of their degree into X. Yes? That's my first bullet point. Now, the second bullet point is, for every vertex, I roughly know its degree into X. Yeah? So I have a linear function, which is a proxy for my objective function. I can now sum over all of the vertices that are not in X of my estimator for the degree into X and get a pretty close approximation to what the value of the cut is. But this is a much nicer function because it's a linear function in the variables, do I go into X or not? Yeah, which means that I will be able to formulate the following ILP for max cut. I now have a variable xv for every vertex. Yeah. Now I'm trying to maximize the size of the cut. What is the size of the cut, assuming that my degree estimates were okay? Well, it's the sum over all vertices that are not in the cut. So it's 1 minus xv. And so if I'm not in the cut, I get my degree into X, then I should be getting d hat of v. Yeah? But now here is a problem. If I just blindly choose vertices that have, now what I want to do is I want to pick the vertices with highest d hat of v and put them outside and set them to 0, because that will optimize my objective function. Yeah, but now I get a problem because I'm going to get some cut that would be great if the degree estimates for that cut were actually correct. But I have no guarantee that that happens, but I can force my degree estimates to be correct by making them linear constraints. In particular, I can just make linear constraints that say that the degree of every vertex into X is close to the corresponding d hat. So here are these constraints. Notice that the degree of a given vertex u into X is just the sum over all v's in the neighborhood of u of xv. This is the degree of u into X. Yeah, and now I want this degree to be at most d hat of u, which I know, plus epsilon n, and at least d hat of u minus epsilon n. And observe that if my good event happened, then xopt is a feasible solution for this ILP. Yes?
So here we are maximizing this estimated value for the vertices we don't know the degree of, right? So the objective function is maximizing the expected value for the variables which are not in X.
Yes. Okay, you can think about it like this. We assumed that all of the good event happened. And assuming that the good event happened, there is some unknown X, and we have d hats. They are not random variables anymore. Like conditioned on the good event happening, we now have some d hats that are the degree of every vertex into some unknown optimum solution. We don't know the optimum solution, but for every vertex, we roughly know its degree into the optimum solution. That's our d hats. Yeah. And now I'm saying, well, for every vertex, either pick it or don't pick it. I'm going to pick, like, there is some unknown X. Let me pick an S. Yeah. My XV variables are, do I pick the vertex into S or not? My objective function is for the vertices that are not picked into S, yeah, for the vertices not picked into S, let me sum of their degree into X. It's a crazy thing to do, right? But now I additionally want the following thing to happen. I want the degree of every vertex into S to be really close to its degree into X. And that's what I wrote an ILP for. But of course, I can't solve an ILP. I can solve an LP. Right? So what I end up with is a fractional solution to an ILP. And after lunch, we're going to round it. So this is a good place to stop. Ask questions.
So here you are taking those X that you're trying to maximize the expected value of variables which are not in X. And for the variables and for other variables, you're seeing a degree in X.
So you shouldn't think of this as something randomized at this point. Like at this point, you should be thinking something completely deterministic. As in, the randomized part already happened, which is like with some probability, our estimators are correct. We now proceed under the assumption that our estimators are correct. Yeah. So imagine there is sort of no expected value or anything at this point, right? Imagine that I give you a graph G, yeah, and in that graph there is some unknown set X. I don't know it. For every vertex, he has some neighbors, right? I mean, he has some neighbors. I know what the neighbors are, but I don't know which neighbors are in X and which neighbors are not. Yeah. For every vertex V, he has some true degree into X. I don't know this true degree. I do know some estimated degree. This should be dx of V. This is better, yes? So dx, yeah. So I know that there is some true degree of V into X, which I don't know, but I have some value d hat of V into X with the promise that my estimate is pretty good. Yeah, this is, yeah. And now what I want to do is I want to say, let me pick some set S. So I have my graph. I want to pick some set S with the following property. On one hand, it maximizes the sum of all the vertices not in S of their degree into X. But it's not their degree into X, it's their estimated degree into X. Yeah, so I have some values for what is my estimated degree into X. But the second thing I want to make sure is that for every vertex, his estimated degree, or his actual degree into S should be close to his estimated degree into X. Yeah. Yeah, and that's what I wrote an ILP for. We cannot solve the ILP. If we could, we would pretty much recover X. Yeah, but we're going to recover something that is almost as good as X. Okay. Yeah.
So the final X that we receive after solving the set, how will it be related to the original set S?
So the final, it's going to have a cut, which is at least the cut of X opt minus epsilon n squared. Yeah, so that's the only thing we're going to know. Well, the things we're going to know about it is that that the degree of every vertex into that set is going to be close to its degree into X opt. Yeah. So you end up recovering it like we will end up recovering a set whose 1 minus xv times d hat of v, like that sum, is fairly close to what you would have gotten if you plugged in X. And furthermore, so you're going to get, you're going to get an integral solution to this LP, but with like 2 epsilon instead of epsilon. Yeah.
Necessary to find ILP? I mean, I'm just wondering that given a property that S estimates the degree into that. I mean, what if we sort of consider all possible partitions of S?
Yes.
Right, and then we we score each partition by saying how much degree from the entire graph is coming into this part of the partition, and we take the best out of these partitions by doing it. So would that work?
I'm not sure I understood your strategy.
Suppose I consider a partition of S.
What is
So S is a random sum.
S is okay. S is this is S. Oh, so now S is a different S. Okay, so S was the sample that we picked initially. Okay.
So now I'm saying to consider all possible partitions of S.
Okay.
And for every partition,
yes,
that the score of the partition is the total degree from G from the entire V into that partition. That's the total number of edges.
Okay, so you take some S, you partition S.
X and S.
Okay, all right, okay.
And then I calculate EVX and EVS minus X.
Okay.
Right, and I take the best out of. Oh, sorry. Oh no. I was trying to see if I could get to the best possible partition. No, sorry.
Okay, well, we can take it offline maybe. Yeah. So this is not the only algorithm. Like once you have the first sample, there are multiple ways of getting to the end. I think this is the cutest one, but. Okay, so lunch. better? Can people hear me now? Okay, great. And we can use. Oh my God.
You said you were going to be cut.
All right. Oof. It says throws me off. All right. All right. So what we did before lunch was we were shooting for a 1 plus epsilon approximation algorithm for every value of epsilon greater than 0 for the max cut problem in graphs of minimum degree c times n. And we observed that the optimum cut has size omega n squared, and that therefore to get a 1 plus epsilon approximation, it is sufficient to find in polynomial time a solution that outputs a cut of size opt minus epsilon prime n squared, right? So for a 1 plus epsilon approximation, additive epsilon n square approximation is sufficient. Then what we observed afterwards was that if you pick a sample of size about log n vertices, or log n over epsilon square vertices, and then for every vertex, you look how many of the sample vertices are in the neighborhood of this vertex, then we can use that to estimate how many neighbors each vertex has in the optimum solution. So there is a fairly low, but not too low probability event that all of the vertices in our sample are actually in the optimum solution. And if that happens, we can pretend that we're sampling the vertices from the optimum solution, which means that we can use this sample in the way that I just described. For every vertex, you can count the number of, for every vertex, you can count the number of neighbors that vertex has in the sample relative to the size of the sample. If you scale that down by the size of the sample and scale it up with the size of the optimum solution, then that will give you an estimate on how many neighbors the vertex has in the optimum solution. And then, I did some math with typos in it, which were confusing. But what can be shown using a Hofting bound is that with high probability, all of our estimates are pretty close. So what does high probability mean? Close to 1, with probability 1 minus 2 over n. All of our estimates, like each of the degree estimates, are off from the true degree into x by an additive term of at most epsilon n. Yeah, so in particular, I guess I can do it on the iPad. So we from now on, yes, we just assume that there exists some optimal solution x such that for every vertex v, the estimator degree of v, which is our estimate for the number of neighbors into x, is between the neighborhood of v intersection x is just the degree of v into x and the degree of v into x, but here we have a minus epsilon n term. Here we have a plus epsilon n term. Yeah, so basically we have reduced the problem of 1 plus epsilon approximating or finding an additive epsilon n approximation to max cut to the same problem with the additional promise that we have these degree estimates that are close to correct. And when I say degree estimates, of course, I mean degree into X. All right. Now, we formulated this funky LP. The LP says the following. Let me have a variable for every vertex. Do I pick the vertex or do I not pick the vertex? And my objective function value goes like this. Every time I do not pick the vertex, I get paid. How much do I get paid? The degree estimate into X. If I pick the vertex, I get paid nothing. Yeah. And what are the constraints? The constraints are that if I look at the vertices that I do pick, the degree of every vertex into the vertices that I do pick is close to the estimate of the degree of the vertex into X. Yeah. So if what we're saying is that for every V, come on, there we go. For every V, d hat of V is pretty close to n of V intersection S, where S is the set the ILP finds. Yeah, so S is the set that is given to us by the variables of the XV variables in the ILP. Okay. So of course we cannot actually solve. So the first observation we want to make is that the unknown optimum solution X is actually a feasible solution for this LP, and its objective function value is fairly close to the actual cut. Okay. First, why is it feasible? So now look at the constraints. Pardon?
We assume that there is such X.
Exactly. So the X that we assumed that it exists, we assumed that it satisfies these inequalities, this inequality here. And then if you just rewrite this inequality in terms of which variables are 1 and which are 0, you just get precisely this inequality here. Yeah. So this inequality here and this inequality here are the same inequality. They're just written in different ways. Okay. Now, what is the value of X opt when seen as a solution to the ILP? Right? So the value, I mean, when I mean value of, so what is the value of the vector of x's corresponding to the actual solution X? Yeah, so there is some set X, that's the optimum solution to the cut. It has a vector of like a 0, 1 assignment to the variables that corresponds to it. And I ask, well, what is the value of the ILP of this solution? Yes?
It should be very close to the actual delta of X, because the only error you're getting is from decay of V.
Exactly. Yes. In particular, we know that delta of X, yes, is equal to the sum over all vertices V in VG of the degree, or not the degree of V, this is n of V intersection X times 1 minus XS. XV, this is what here we go. Yes. So if I set XV to be 1 if it is in X and 0 if it's not, then notice that if I sum over all the vertices, and I count the vertex if it is not in X. So if it's set to 0, then I count it. And if it's set to 1, then I don't count it. And then if I do count it, I get the number of neighbors it has into X. Yeah. Then I get actually the cut size. Yeah. But now I know that n of v intersection X is at most. So I want to say that. No, I want to go in the other direction. I want to say that this is less than or equal to, yes, the sum, and I go over all the vertices in VG. And now all I can do is I can replace the n of v intersection X with my estimate for it. Yeah, and that is just d hat of v, but it's not d hat of v, right? It's n of v intersection S is at least n of v is at least d hat of v minus, or well, in this case it should be plus epsilon n. Yes, because I want the crocodile to point to the right. Yeah, to the big guy. So I need to add something. Okay, and now I multiply this by 1 minus xv. Yes, and if I pull the epsilon n out, I just get equals epsilon, or let's say at most, because some of these guys get canceled. It's at most epsilon n squared plus the sum over all v of d hat v into 1 minus xv. Yeah. And this is exactly the objective function of the integer linear program. Yeah. So in particular, if I now move the epsilon n square over to the other side, I get that the objective function value, let me copy it. Oh, let's see. My iPad is not made for doing this live. Here we go. Right, so now all we need to do is to take this and move this to the other side. And here we are, right? So in particular, the objective function value is at least the actual cut size minus epsilon n squared. Yeah. So xopt is a feasible solution to this ILP, and its value is the cut size minus epsilon n squared. So when we solve the LP, we will get a feasible solution with at least this value. But it's an LP solution. It's not an ILP solution. Now, we only know how to round ILPs in two ways. I only know how to round ILPs in two ways. There are many more clever ways to round ILPs. I'm just not an expert in rounding ILPs, but the ways I know is either greedy thresholding, just like everything bigger than this goes up, everything lower goes down, or this is a probability, just round it one way or the other. So let's do that. Yes. So what we're going to do is do the randomized rounding trick, right? We have a variable xv that is between 0 and 1. Add each vertex v to my solution x. It should be s so that I don't confuse it, with probability xv. Yeah. And now we ask ourselves, well, what is going to be when I get this set? I need to ask the following things. One is, what is the expected value, or what will the value of the ILP objective function be? And the second thing is, will this be a feasible solution? What will the degree of every vertex into this rounded set be? Okay, so first, let's look at the expected value of, let's look at the expected value of the ILP objective function, right? What is this going to be? It's going to be the sum over all vertices in G of 1 if the vertex is not in X times d hat of V. Yeah. But what is that? That is just the sum over all vertices that are not in X of d hat of V. Yes. But that's just opt-LP. Yeah, that's literally what we just did. But opt-LP is at least the delta of X opt minus epsilon n squared. Now, I'm not going to do this. I'm just going to make you believe me. This is the sum of n random variables, each one of which has value between 1 and n. And if you apply Hofting inequality to it, what you're going to get is with high probability, you're actually pretty close to expectation. So, I mean, the expectation is what you want it to be. This is a sum of many independent random variables. They are not 0, 1 random variables because every time you flip one of them, right? Like for every vertex that you put either into V or not into V, that's a 0, 1 random variable. But when you put it, whether or not you put it, if you don't put it into V, you get d hat of V. So it's not a 0, 1 random variable, it's a 0 d hat of V random variable, and d hat of V is between 0 is between 0 and n. Yeah. So now if you know that okay, there's n random variables and they're all between 0 and n, you plug it into Hofting, you see what you get, Well, you see what you get, I mean, you get what you want to get. Yeah. You get that with high probability, you're not more than another epsilon n square term away from expectation. If expectation is the cut minus epsilon n squared, well, you lose another epsilon n squared. Okay. Now, let's say that this is the good event 3, and now the only thing we're left to prove almost is that for every vertex U, it holds that its degree into this rounded set is fairly close to the estimated degrees. Yeah. Well, okay. So first, we want to say, well, what is the expected? Okay. So first, what is the expected degree of U into the set X? Yeah, this is again a sum of 0, 1 variables. For every neighbor of U, we include it in X with probability XV. Yeah, so the expected intersection of the neighborhood of U with X is the sum over all neighbors of U of the XV variables. But that is precisely what our LP was saying. Yes, this LP says that for every vertex in U, for every vertex U, if I sum over all V in its neighborhood, the XV variables, I'm going to get a number between d hat minus a little bit and d hat plus a little bit. Yeah, so the expected, so for every vertex, the expected number of X vertices in its neighborhood is the correct thing. And now again, Hofting tells me that you're going to be close to expectation with high enough probability that if I take union bound over all the vertices are no more than another epsilon n off from this bound with high probability. And I'm not going to do it. I mean, I tried to do it last time. It went terribly. It's one of those things that it's just better to do it yourself. Right? Like, so we know that the expectation is the right thing. Apply Hofting and union bound. All the vertices will have close to correct number of neighbors in X with high probability. Yeah. Where close to correct means we pay another additive term of epsilon n. And now we ask ourselves, okay, what happens if both of the good events happen? And now I just want to compare, then I have a set X, yeah? And I just want to say, what is the cut of X? Yeah, well, I know that the cut of X is the sum of all vertices that are not in X of the number of neighbors this vertex has into X. Yeah, but because for every vertex the degree estimate is close to correct, I can replace n of u intersection x by the degree estimate minus a tiny error term. Yeah, because the good event happened. And now I take the minus 2 epsilon n out, and this is the sum over all u not in x of d hat of u. Yes? But the sum of all u not in x of d hat of u is at least the cut of the optimum, is that at least the LP opt minus another epsilon n square fact, another epsilon n square term. So which means that the cut that I output is at least as good as the optimum cut minus some epsilon n square vertices. That minus, it shouldn't be epsilon square n. I guess it should be somewhere here. It should be epsilon square n squared. Yeah, there is a square here as well. Finding out. Let's see. There we go. Yeah, better. Okay, so what's the overall algorithm? You repeat a bunch of times, like n to the 1 over epsilon square many times. Pick a sample. Sample it of size. Take a sample of size s uniformly at random. Use the sample to compute the degree estimates. Using the degree estimates, you formulate and solve this du hat LP. Apply randomized rounding to get your set X. Now you have a set X, you keep the best one. You repeat many times. Now, this set X is only going to be good, right? It's only going to give you this set X is only going to give you a large cut if this initial step, sample S uniformly at random, succeeded. And that sample actually was inside the optimum solution, which happens with low, but not too low probability. But now when you're repeating this n to the 1 over epsilon many times, at least a few times it's going to actually happen. And when it happens, with high probability, the X you get will be good. And therefore, you now succeed with high probability of getting a 1 plus epsilon approximate solution to the whole problem. Okay, so this is a good place to take a little bit of break, take some questions, because then we're going to flip to something completely different. Well, still max cut, but a different algorithm for max cut. Any questions? Okay, so if you fell off the train, right? If you fell off the train during the last half hour or so, this is a good place to wake up again, because we're starting from scratch. We're going to do something completely different, and at least the stuff that we're going to be doing in the beginning is somewhat basic, like doesn't take too much concentration. It's going to get bad again, but okay. So we've been talking about linear programming. Let's generalize linear programming. This is a wonderful tool. If you have a hammer, you keep looking for nails, you find nails, you're very happy about it. But what would make you even happier? A bigger hammer, right? And that's what we're going to do now. So this is called semi-definite programming. And when we did linear programming, what was going on? We had variables that were real valued, and you could have an objective function that is any linear function in your variables, and you have constraints that are linear inequalities in any linear combination of your variables. Now we're going to do something fairly crazy. We're going to say, well, suppose my variables aren't real numbers, but they're vectors in Rn. And so every variable is a vector. Okay, sure. Now, what are we going to be allowed to do? We want to optimize, so maximize or minimize, not a linear combination of our variables, because a linear combination of vectors is a vector. What does it mean to maximize a vector? Yeah, we're going to maximize or minimize a linear combination of dot products of our vectors. The dot product of any two vectors in Rn is a number, so it makes sense to like maximize or minimize that. So you have some, optimization program where what the solver has to do is to make vectors point all over the place, so that after you take their dot products and combine them by multiplying by some constants, that gets maximized or minimized. And what are your constraints? Your constraints are linear combinations of dot products of your variables again. Yeah. The way it's written is with equality, that like all of your constraints are equality constraints. Makes it easier to work with later, but actually you don't lose any generality. This is a funny thing. Why is that? If I want to make an inequality constraint, right? Suppose I want to make a constraint that this is less than or equal to bk, I can just make a new variable, vi prime, that doesn't contribute at all to my objective function. And then what I can do here, oh, this was not what I wanted. What I can do here, I can like say, plus vi prime times vi prime. Yeah, now I can choose vi prime to be whatever I want, but vi prime, a vector dotted with itself, will always be something positive. Yeah, so effectively I'm now encoding a, less than or equal to constraint here. And if I can do less than or equal to, I can also do greater than equal to, because I could do minus vi prime times vi prime and get it in the other direction. So the fact that I have equalities here doesn't really cost me anything. Okay. Okay, so yes?
What sort of geometric shapes do these equality constraints correspond to?
Please don't ask me. I have no idea. Yeah, I'm like, this is the part of the class where I'm definitely talking about things I don't know. So good source for this. So okay, so this lecture follows the, I think chapter 7 or 8 of the approximation book of Williamson and Schmois. So anything correct I say is due to them. Anything incorrect is due to me. So okay. We made SDPs, right? Do they? It's not even clear that this generalizes linear programming, right? I mean, your variables are vector valued. Like, is this really a bigger hammer than LP? Okay, let's check that it is. Well, suppose that all of our linear functions on dot products don't ever use the cross terms. They never use like VI, VJs. Yeah, they only are linear combinations of VI, VI. Yeah, then effectively the VI, like the VIs are just scalars, right? You're just choosing their length. Now, of course, they can only be positive, yes, but I can encode a single real valued variable that can be either positive or negative as two non-negative variables. Like x is equals x1 minus x2, where x1 is positive and x2 is positive. Now x can be anything. Yes. So in particular, I can this optimization problem is strictly more general than a linear program. Why does it get more power? Well, it can kind of encode the and of two variables. Like this sort of dot product, you're saying, well, are these two things both pointing in the same direction, or are they pointing in the opposite direction? And the LPs have a hard time of capturing that. Now, the wonder of LPs is that you can solve them in polynomial time. And for STPs, we can also solve them in polynomial time. Well, kind of. The well, kind of means that you can get a 1 plus epsilon, you can get a 1 plus epsilon approximation in polynomial time, and the dependence on epsilon is very good. I think I don't remember if it's like poly 1 over epsilon or poly log 1 over epsilon, but it's sort of, it's so good that most of the time you don't actually care that it's an approximation and not an exact solution. And like, if the STP has integers in it, then, you know, once you get it to the correct precision, you can just round it to the nearest integer and show that that will give you the correct value. So for all practical purposes, we can solve STPs in polynomial time. Now here is a wonderful approximation algorithm for max cut. We just had a half approximation that just picks a cut at random. That half approximation has a nice property that it always outputs m over 2 edges, right? But you know, if you're comparing, then we're comparing the value of the algorithm to m and using that to compare it to opt. Maybe you can get a better bound on the approximation factor if you're actually comparing what's going on to opt. So for random cuts, that doesn't help out, but if you do something smarter, it does. Maybe we could hope for a p-TOS, right? We managed to get a p-TOS for vertices for graphs where every vertex has large degree. But unfortunately, you can show that this is not possible. So a 1.0001 approximation for max cut would actually imply that p is equal to np. So what we're going to do now is we're going to get an algorithm that is a 0.878 approximation. So it's an approximation algorithm with ratio that's really close to 1. What does it mean to have an approximation ratio that is less than 1? It's actually 1 over that, right? Like you always, so whatever the cut is, you will output a cut whose value is 87.8% of that cut. Yeah. And it's pretty cool because if you believe the unique games conjecture, whatever that is, then you cannot do better at all, right? Like an 8.79 approximation algorithm would violate unique games conjecture. Yep. Okay, so what we're going to do is we're going to formulate max cut as an integer quadratic program. So an integer quadratic program is just like an ILP, but now our objective function can have some quadratic polynomials in it. And here it goes. For every I have, so for every vertex, vi, I have a variable xi, which is 1 if the vertex is on the right side of the cut, and -1 if it's on the left side of the cut. Okay, can we even encode x in 1 minus 1 using linear constraints for integers? And if we say xi is between I and minus, well, like xi in z and xi is between -1 and 1, I'll be in trouble, right? Because you can also pick 0. So any suggestion for how to encode this using linear constraints? So suppose xi's are in z, right? Like suppose xi's are integers, yes? And I want to encode that it's not just any integer, it's an integer that is either -1 or 1. and I'm allowed to use the linear constraints and that it is an integer. Well, yeah, or multiply by 2 and subtract 1, right? So I say that y, right, like y is an integer which is either 0 and 1, and then x is 2 times y minus 1. Yeah, if y is 0, then x becomes minus 1. If y is 1, then x becomes 2 times 1 minus 1. So that's 1. Yeah. Okay. And why are we now optimizing this weird notion or this weird sum for every edge vi vj? I want to look at 1/2 1 minus xi xj. What is this? Well, okay. If the two vertices are on the same side of the cut, then the xi's get the same value, and I get 1/2 1 minus 1, which is 0. Yeah. If the two vertices endpoints of the edge vi and vj are on opposite ends, then xi and xj have opposite signs. So xi xj is minus 1. 1 minus minus 1 is 2. Divided by 2 is 1. Yeah. So you're now exactly for every edge, you're getting 1 every time the vertices are in the opposite direction. Okay. So in particular, this shows that for any cut, if I set xi to be 1 if you're on the left side, minus 1 if you're on the right side, gives you a solution to this IQP with value which is the size of the cut. And in the other direction, if I have a minus 1 1 assignment to the variables, then setting a to be the ones that are set to 1, then that gives me a solution with the same value. Okay. Now, here's the thing. We can solve semi-definite programming. We can't solve integer quadratic programming in polynomial time. So now we need to make a semi-definite relaxation of this quadratic program. So what we're going to do is we're just going to replace our minus 1 1 xi variables with unit vector variables. So I'm going to say, let's maximize. So for every vertex x vi, I have a vector vi. Yes. For every vertex I have a vector vi, and I'm maximizing 1/2 the sum of 1 minus vi vj, subject to vi's being unit vectors. Now notice that in the vector world, this is a generalization of being either 1 or minus 1. Like in one dimension, being a unit vector means you're pointing this way or that way. But now I can point all over the place. Yeah. Now, is it obvious that this is even a relaxation, right? But for it to be a relaxation, I need to say that for every integer solution to my original IQP, I can get a solution to this SDP with the same value. Yeah. So what I'm going to do is, if I have a solution x1 through xn to the integer quadratic program, I just set vi to be xi in the first coordinate and 0 everywhere else. Yeah, and now observe that vi.vi is equal to 1, and 1 minus vi vj is 1 minus xi xj. Cool. So now we can solve the SDP. And the question is, given the solution, how do I even find the corresponding cut? Or how do I find the corresponding integer variables, right? Like this amount, this is the analog to rounding the LP. If I give you the weird vector variables, how do I find the integer variables that correspond to it? What we're going to do is we're going to pick a random vector in Rn such that its norm is 1. So in particular, we're picking a random vector on the unit sphere. Point in a random direction. This is what happens. Now here's a funny thing. It's actually not entirely trivial to do this. Like picking a random vector, or picking a random point on a circle That's on the boundary of a circle. That's fairly easy, right? You just pick a random angle. Yeah, that's okay. Now, how would you do it in 3D? Like, how would you pick a random point on the boundary of a unit sphere in 3 dimensions? You want to do two-angle analysis. It's exactly the answer I wanted you to give because it's wrong. So here's a funny thing, right? So the first angle is along the first sphere, right? And the second angle is how far up you go, right? So when I give you the 2 polar coordinates, what happens is that I tell you how much up should I go and then how much should I rotate. Yes? And now here's this funny thing. When I point forwards, then when I rotate, I'm going to rotate a lot. So the density of points along equator is really low. The density of the points pointing upwards is really high. Yeah. So I'm going with very high probability. I'm going to be picking points that are close to my poles if I pick random angles. Yeah. And in higher dimension, it gets even worse. Okay. So now that I've convinced you that it's a non-trivial task, let me convince you that it's a trivial task. Turns out that if you just take a basis, right, like the x-axis, y-axis, right, you pick, and you pick every coordinate you pick every coordinate uniformly at random, but not uniformly at random. You pick every coordinate from a normal distribution, like n0, 1. So normal distribution with mean 0 and standard deviation 1. Turns out that you're not always going to get a unit vector, right? You could potentially get 0, or you could get something really long. But you can show that the direction of the vector is uniformly distributed, and I'm going to make you do that for the tutorial, because it's actually not that hard to show. So in particular, like here is the formula for the normal distribution in 1 dimension. If this is what you use, then the direction you end up pointing will be random. Okay. And then you just take the unit vector. Yeah, so in particular, you pick r, and then you take r divided by the norm of r, and that's your point on the boundary of the sphere. Exactly. Okay. So we now picked a random unit vector, and we have these solutions of the VIs. And you remember what was our interpretation of the original IQP, right? Every vertex, every value xi is either pointing left or right. Everyone who points left, I put on the A side. Everyone who points right, I put on the B side. But now that you're on a circle, there is no notion of left and right. What we did is we selected a random notion of left and right. So you pick a random direction on the sphere, and you're saying that everyone in this direction, that's left. Everyone in that direction, that's right. So you pick a random hyperplane through the origin that cuts your space in 2 halves. All the VIs that go one side, that's one side of the cut. All of the VIs that go on the other side, that's the other side of the cut. And of course, how do you check? You don't cut your hyperplane mathematically, right? You just check the dot product of VI with R for every VI, and if the dot product is positive, you go on the A side. If it's negative, you go on the other side. Okay. So we've now defined a cut, right? We've solved the SDP, and we found a way to get a cut from the SDP. So all that's left is to analyze how good it's going to be. Yeah. Well, let's figure out how good it is in expectation. What? This is the rounding. This is the rounding. Yes, you pick a random hyperplane, and then everyone who is dotted positively with the vector go on A side. Everyone who is dotted negatively go on the B side. Yeah. Yep. So now all we need to do is we need to analyze what is the expected size of this cut. Yep. Well, it is the sum over all edges in the graph of 1 if the edge is in the cut and 0 if it's not in the cut. Yeah. So now we need to ask, well, what? So that is just the sum of the probability over all edges of the probability that that edge is in the cut. So all that's left to analyze is for every edge, what's the probability that that edge is in the cut? All right, but that is nothing but the probability that the sine of r times vi is equal to the sine of r times vj. Yeah, because the sine of r times vi determines whether vi goes left or right. The sine of r times vj determines whether vj goes left or right. And what you want is for the two sines to be opposite. Then they go on opposite sides of the cut. Okay, now here is an observation, and that is, you know, the sine of vi dot r depends only on the projection of r onto vi. Yeah, so if you look at the vector vi, you picked r, then you project r onto vi, and you see, does it point in this direction or in that direction? And that determines whether vi goes on the a side or the b side of the cut. And the same thing for vj. Yes. So in particular, whether vi or vj go on the same or the opposite direction now depends on the projection of r onto the span of vi and vj, which is now a plane. Yeah. So I take the vi vj plane, I project r onto that plane, and I want to now study whether the projection of r in the plane. Now what I care about is r in the same or opposite direction as vi, and the same for vj. Yeah, only looking for that projection. And now here is a really cool observation, and this is that pick any circle, right? Like pick any vi vj, that is going to span. That's if I have my sphere, I pick a vi vj, I take the vi vj plane, cut, I get a circle. Yeah. Of course, if I did it in the xy plane, I would get a circle. Yeah. And now I claim that for any plane, if the projection of r onto that plane, the direction is still uniformly distributed along the circle. And the reason for that is that everything is symmetric. If you remember, how did we even pick r in the first place? We picked r by a normal distribution in the x direction, a normal distribution in the y direction, and then a normal distribution in all the other directions. So it should be fairly clear that in the xy plane, so the projection of r onto the xy plane is just a normal distribution in x direction, a normal distribution in y direction. So in particular, that is a random unit vector in the circle. Right? So this is true for the xy plane, but the xy plane is not special. I could have done this along any basis, and if I'm picking uniformly at random from the entire sphere, it doesn't matter which basis I would have picked first place. Yeah. So in particular, the projection of r onto any circle has a uniform direction around the circle. Right, almost done. Because now all we're interested in is the vi vj plane that gives us a circle, and r is pointing somewhere in the circle. And what we care about is vi dot r, or does vi dot r and vj dot r have the same sign or not? And the geometric way of viewing this is the following. You have the circle, r points somewhere, and that splits the circle into two half circles. The ones that point in the same, the ones that will get positive, and the one that will get negative. Yes? And now what you can do is you can, instead of asking where does r point, you ask where does this line that splits positive and negative, that one is now uniformly distributed on the circle. Does that go between vi, vj, or are vi and vj on the same side of that line? Yeah. So now this line, it rotates around, and then you ask yourself, does vi and vj, do they get split by this separator, or do they not get split? And we are interested in the probability that that happens. Okay, now notice that if you have a line, yes, like if I have 2 pi options for where the line could be, right? It could go all the way around. But you know, once I have gone half a circle around, I'm back to where I started. So I only have pi options, not 2 pi. I only have pi options for where the line could be. So it's now enough for us to look at half of the circle. Yeah. So in particular, let's just rotate the circle so that VI points in the x direction, VJ points somewhere in the top hemisphere. I can do this. And now I'm interested in the half of the line that splits them. Does it split them or does it not split them? Yeah. And now if I look at the angle between VI and VJ, yeah, the probability that it gets split is proportional to the angle between VI and VJ. Yeah. So if the angle between VI and VJ is alpha, then the probability that they get split is alpha over pi. But we don't have alpha, right? Alpha is some angle between 2 vectors. We don't have the angle but we do have their dot product. And the dot product of 2 unit vectors happens to be cosine of alpha. Yeah. So in particular, the probability that the edge UI uj is in the cut is alpha over pi, which is arc cosine of VI VJ over pi. Okay. So now let's write our expectation, right? Remember that the probability that UI uj is in the cut is arc cosine of VI VJ over pi. And the reason we were figuring out this probability was that the expected size of the cut is the sum over all edges in the graph of the probability of them ending up in the cut. So this is nothing but the sum over all UI uj arc cosine VI VJ, which I will shortly show to you is at least 0.87 times 1/2 1 minus VI VJ. So in particular, what I'm going to do is, you know, arc cosine, I will now forget about the fact that VI VJ are vectors. And I'm like, this is just arc cosine of x divided by pi. I mean, there's some value. Yeah. And if I can show to you that arc cosine of x over pi is always at least 0.87 times 1/2 1 minus x, yeah, then I'm done, right? Okay. I'm not going to show you, but I'm going to show you, right? I'm not going to prove this to you, but I've plotted these two, and you can too. So if you plot 1/2 1 minus x, you're going to get this green line, yeah? And if you plot arc cosine of x over pi between -1 and 1, you're going to get this blue curve, yeah? And what you're interested in is what is the smallest the blue can be relative to the green, and it turns out to be at most 0.87. Okay, now if you know your trigonometry, you can put in, you can do some variable substitutions and prove this analytically, but I don't want to. Yeah. So then you're getting that this is at most 0.87, the sum times 1/2 minus VI VJ, which is of course 0.87 times opt SDP, because this was just the objective function value. And that actually concludes the whole algorithm. We only showed that the expected value is what we wanted. But again, opt is integral. Yes, or like the value is integral. You can use Markov inequality if you want to get polynomial probability of achieving at least the optimum. Yeah. Okay. Questions? The alpha and the pi part. This part. Okay. So, okay, let me do it over here maybe. Okay, so we have some circle, and there is some VI and VJ in that circle. Yeah, and we're picking an R, and we're interested in R.vi and R.vj. So is it okay that when I pick R, what happens is that I'm splitting my circle into two parts. The one on the side of R ends up being positive. The one on the other side ends up being negative. Yes. So really, what you care about is whether this line splits the two green vectors or not. That's like if it splits them, then they're on opposite sides. If it doesn't split them, they're on the same side. Yeah. Okay. Yes. So this is R. Yes. The thick red line is the line perpendicular to R. Yeah. And now I'm saying that, well, I mean, it's a circle, right? So everything is symmetric. So let me rotate the circle so that the two green lines, like one green line is pointing to the right and the other one is pointing somewhere in the top half. Yeah. Now my red cutting line, yeah, is still uniformly distributed in the circle. Yeah. But I'm only interested in the top half of the red cutting line. Like if I'm cutting here, I'm only interested in this part. Yeah. And this part of the line is uniformly distributed along the half circle. Yeah. Which means that I have pi options for it. Yes. And if that line ends up between my two green vectors, then they do get split. Yes. Now, the angle between them is alpha. Yes. So the probability that it ends up between them is alpha over pi. Yeah. And then after that, we're just observing that alpha is arc cosine of VI/Vj. Yeah. Yeah.
Why did we formulate everything in Rn when we could have done it all in R1?
Because SDPs cannot like the solver cannot solve things with variables in R1.
It's a subset of all the cases of SDP. So if SDP is defined for any vector.
No. So where Rn is the number of variables you have. If you have n variables, your variables are vectors in Rn. It's a very good question and a subtlety that I didn't mention, right? Like where does this Rn come from? If you have n variables, your variables are vectors in Rn.
So how did that help us in the formulation? As in, did it show up in some calculation?
No, it doesn't help you. It works against you.
So they might need space to have the vector. So
as in, how does it help the solvers? Don't ask me. Okay. Okay, I think we're done for today.
Thanks. All right, so for the Zoom audience, that's a wrap for now, and we will reconvene at 4:30 for the tutorial as usual. For the in-person audience, there's still half an hour to the coffee break. So I have a nice way of spending that half an hour. So if you'll just follow me once we're out of this room, we have a Center for Creative Learning and they have some really cool stuff. And I would like you to see it. And it's not very far from here. It's just across to the other auditorium. So that's a good way to kill some time and have some fun. And then we'll come back at 4 for the coffee break, and at 4:30 we will do the tutorial. And by the way, the materials for today are all up on the usual website, so you can find the tutorial, the notes, the videos, yes, all of that good stuff. Thanks. All right.